Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So today, before anything, I just want to remind people, I sent a message about it earlier, but I did put out the solution for assignment 1. I mostly do this because I want to make sure you have some expectation of how you may present some of your solutions. They may not necessarily match exactly mine compared to yours, and I'll be hopefully have those marks back to you within the next week. So just keep that in mind. Now, the main thing I want to talk about today is this pumping lemma. So last day I introduced this to you, and it's a rather complicated looking statement. And I'm hoping that by the end of this, I should be able to dispel some aspects of it so that you can actually use this to prove that a language is not regular. So I just want to remind you, and I want to give you an intuition about what this pumping lemma exactly means in relation to our proof. So the first thing is that it says that for all regular languages, there exists this pumping length. And remember, in our proof, this ended up being, for some DFA, it was the number of states of that DFA. Where for all the strings that get accepted that are recognized as part of that language, if they are of sufficient length, meaning they're at least the pumping length, there exists some way I can decompose or divide the string into 3 parts, X, Y, and Z, such that the Y part isn't empty. That means its length is at least 1. The first part of the string, this XY part, is at most the pumping length. So it means that this occurrence of this Y has to happen some point before the first P symbols, or is of the first P symbols. And this last condition, this is the one that usually the people that call this pumping lemma, they call it the pumping lemma, it's for this third condition mostly, is that for all k greater or equal to 0, it means that x, y to the k, z, that means I repeat repeat y k times, or I remove y altogether. That's when k is equal to 0. And this will belong to the language. So that k is the number of times I pump the string. Hence why we call it the pumping lemma. So I thought I would just motivate quickly before we proceed to using this pumping lemma to just give you an idea what this pumping exactly means, just within the context of that. So I thought I would give you a DFA. So this is the DFA for, let me think here. I kind of just drew this offhand. This DFA here, what language does this DFA recognize? Can somebody tell me? I want you to think about it. I'll give you a hint, it involves ones. Well, let's see. So we know that it takes a 1 to get into here. So let's see, we got 1, and then I can read another 1 to get here. Then I can read another 1 to get me here. Then I can also do a 1 again and a 1 again. So notice that I take 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that the number of 1s that I need to get here is it even or odd? It's odd. It's odd. Yeah, so notice that the number of 1s. Now, actually, just to make this a little bit more easier for me to spot, let's think about this. Actually, I need to be a bit careful here. I think somebody pointed out something that's rather interesting about this DFA. Is it odd, or is there something just general about this? Because notice I can go 1, then I could go to 0 to get me back here. I think that all we I'm just trying to think, because I wanted to just see what we could think about with this. It's more of an open-ended discussion. Maybe it's just that it ends with a 1. Maybe that seems to be a reasonable way I can infer from this. Because notice that I can read a 1. And then I can read a 0 or 1. Notice it's a 0 or 1. If I change the DFA slightly, like say if I do this instead, make that a 0, and I get rid of this, now does it do what we suggested earlier? That it reads how many 1s to get to a final state? Always an odd number? Yeah, so notice I go 1. Then now you'll see that now it has to read an odd number of 1s. So I thought I would do this just to remind you of what we do with the DFAs and what it means for a language to be recognized by a DFA. So I want to show you just a couple of examples just quickly just to illustrate the point of this pumping lemma. So I have a couple strings here. These are two different W's that I have as per the pumping lemma. So they're both of sufficient length because notice that the number of states I have here is 2. Now, we have to be, so remember, all it says is that there's a way I can write W to be X, Y, or Z with those conditions. And you always have to be careful about way you look at this. Because remember, X and Z, they may be empty, but Y isn't. Because remember, Y can't be the empty string. So when you look at this, you have to be a bit careful. So when you look at this and you try to look for what X, Y, and Z are, let me think about it here. So let's see. So notice that, remember, the first condition is that Y isn't empty, so we know it's at least one symbol. And since this example, there's only 2 symbols there, that satisfies that condition. But the third condition, this is the one that's going to determine what Y might be, is notice that X, Y to the K, Z must be in the language. So whatever symbol I select to be Y in my example here, keep in mind, Y could be a collection of symbols too, but I don't have a whole lot to work with there. So if, for example, I make K is equal to 0, that means Y isn't actually a part of the string anymore. But remember, it has to be in the language. So for example, notice that I can't make Y be 1, because notice that if I get, now first the problem here, of course, is that if I make K is equal to 0, I eliminate the 1, and that means I take a 0, and that doesn't get me into the language, right? Because it'll keep me in Q0. However, if I take Y to be, say, the 0, and I let X be empty, and I let Z be the 1, notice that I can pump 0, right? Look, I can keep reading in more zeros. In fact, I don't even need to read 1 0, right? I can read no zeros, and I can go right to the final state right here. So this would be one example of a way I can decompose the string Y so that it's written as X, Y, Z. So notice that it isn't just that any way I can decompose them, it works like this. It has to be that there exists a way to do it. Just like this one here, this one is a much longer string, but the same principle applies. So notice that I'd like it so that it still remains in the language regardless of whether I pump the string. Sorry, if I pump the string, it means I don't include it, or I repeat it once or more. So notice that I can make this Y again, and I let X be empty, and the rest of this I make Z. So notice that by doing this, remember, Y has to occur in the first P symbols. That's why I've selected Y in the way I have. So notice that I can't necessarily make this be the case. I can't make it 1, because if I make K is equal to 0, that's never going to get me to Q1. However, if I make it 0, I can stay in Q0 as many times as I like, or not at all, and I could go right to Q1 after I read a 1. And of course, when I read, say, the third one here, so I go 0 as many times as I like, I go 1, then I go 0, then I go 1, then I have 0, 0, 1. So notice that this is another example I can decompose X, Y, and Z. So are we okay with that? So the idea is that I can pump Y. So I can pump, this is what I mean by the pumping lemma. I can pump Y. So I can pump it 0 or more times. That's what the third condition there is. This is why we call it the pumping lemma. So this is something that's true for any regular language. Are we okay with that? So I just wanted to give you a little intuition. This was a part of the proof last day. It's just that I wanted to give you just a concrete example so you can see what I mean. So that brings me to talking about how we're going to use the pumping lemma. So just as a reminder, remember the pumping lemma is a property of regular languages. So the big strategy here is that if I tell you that if L is regular, then L satisfies the pumping lemma. That's just true of any regular language. It satisfies this pumping lemma. It's a property of regular languages. So what you could do is you could take the contrapositive of this, So if you take the contrapositive, so the contrapositive. So if I take the contrapositive of this statement, then you could say, okay, well, if L does not satisfy the pumping lemma. I'm just going to abbreviate it as PL for this lecture because it gets a little lengthy after you do that so many times. So if it doesn't satisfy the pumping lemma, then L is not regular. So just watch carefully the reasoning here. So this is going to be our game plan, is we're going to try to show that a language doesn't satisfy the pumping lemma, and then that will mean that it's not regular. Now you might ask, how are we going to do that? Because that looks like a rather complicated looking statement. And this is where you're going to need your discrete math thinking here. You got to use your logical quantifiers. You got to think about this carefully. So I'm going to do that right now. And I want to just kind of walk you through this process. Okay. So if I have so remember, it says there exists pumping lemma, pumping length P such that for all strings W in the language with the length being at least P, there exists a way to write it this way. And there's these three properties here that have to be satisfied. So what I'm going to do is I'm going to negate this statement. So I'm going to say for all. So I'm going to replace the there exists with for all. Whenever I see a for all, I say there exists. There exists. And when I see there exists there, I say for all. And just to be the matter of me being picky about these things, for all ways to write W is equal to X, Y, and Z. And then the last thing is at least one condition fails. So at least one of these three conditions has to fail. It says condition false. It sort of melted there. My apologies. So I'm saying there's at least one of these that has to fail. Now you might ask, okay, Dan, which one, so you got to think about this. You have to be very careful about this. So when I say there's at least one condition that fails, typically when we try to prove a language isn't regular, we like to use these first two properties. These ones we like to take as assumptions. And then we like to break it using this third condition, the one that says that a string can be pumped. We're going to try proving that there exists a W that can't be pumped. So we're going to try our best to come up with a W that's going to not be able to be pumped, as in the third condition of the pumping lemma. So here's the game plan. So now I've kind of given you the idea of what we're going to try doing. And this is how generally these proofs are going to go. I'm going to assume that there exists, so I'm going to assume that the language is regular as per the conditions of the pumping lemma. And then what I'm going to do is I'm going to proceed to try to select for you a string W, assuming that this pumping length exists. I don't know what it is. It just has to, it could be any, it's just a part of the pumping lemma, right? It's just some constant that exists. My goal is I'm going to try to find a string that is in the language with the length at least the pumping length. So this is under the assumption that the language is regular. And then what I'm going to do is, based on this string, I'm going to try to show you, regardless of any way you can decompose W into the three parts, X, Y, and Z, that at least one of these conditions fails. And typically when we do this, because we're going to be using contradiction, I'm going to take these two as givens, typically, and then I'll try to break it by showing you that there is no string that can be pumped, as in I select a K, so I select a K here. So I select K, select K to show X, Y to the K, Z is not in the language. and then I get a contradiction. So the whole idea here is that I'm going to assume, using contradiction, that the language is in fact regular. I'm going to use the properties of the pumping lemma, and then I'm going to work my way down to try to get me to where I can isolate out a string that I get to pick. And my goal is to figure out some way that it won't be able to be pumped. And that's how I'm going to get the contradiction typically. There's a couple of finesse and tricks to doing this. I have to warn you, there's a couple of things that you have to keep in mind when you're doing these types of proofs. Namely, you want to use these two facts to help you, not work against you. For example, remember the intuition is that the W can be pumped, right? But it has to occur in the first P symbols as per the pumping lemma. So what you want to do is you want to try to figure out a string that will contain X and Y and they have the same symbols in them. That's usually the trick that you'd like to use when you're trying to show that a language isn't regular. So the way I like to think about this is that it's almost like a game. So this is one I know Hopcroft also talks about in this way. They talk about like a two-player game. So you can imagine that you're playing against somebody and you don't know really necessarily what the pumping length is. So they give you some pumping length. You don't know what until they give it to you. So it's some arbitrary P. And then your job is to, you present a craftily, maliciously made string W, assuming that it's regular. And then there's going to be some arbitrary way that the person that gave you this P is going to be able to decompose this. And you don't necessarily know which one, so you got to account for all possibilities. And then your job is to figure out what K is, and then if you do, you win. So the idea is, everybody got a general idea what we're going to try doing? Once we see the first example, this should hopefully help a little bit. So just keep in mind the quantifiers. So remember, my goal is to assume the pumping lemma is true for the language, and then I'm going to use properties of the pumping lemma to break it. Are we all okay with this? Give me a thumbs up. At first this looks a little intimidating, but I assure you, once you get the general gist of this, it's actually not that bad at all. Okay, so let's do, let me just do an example with you. So let's do an example. I'm going to consider the following language. So I'm going to consider, I'm going to call it L-eq, like this. This is a classic example. And we're going to assume I'm given the following language. So I'm going to have it where I receive M zeros followed by M ones. So that's what our language is going to be. And I'm going to prove for you that this isn't regular. That should be a subscript. L-eq is not, it's not regular. So that's what we're going to prove. We're going to use the pumping lemma against itself. Okay? So this is why I describe the pumping lemma like a tool. Is that it gives us something that we can play around with to figure out if a language is regular or not, because every regular language satisfies the pumping lemma. Okay, so now, like I said, I'm going to use contradiction here, so just carefully follow me. So I'm going to assume language L-eq is regular. Then by the pumping lemma, the pumping length P, as in the pumping lemma, exists. So I know that exists. Now, like I said, the general strategy is, so remember, I don't know what P is. I just don't know what it is. So you gotta imagine you're playing against a friend and they just throw something at you and you're like, hey, get it. So imagine I have the P now, so I take the P, and now my job is to maliciously craft a W that's gonna cause problems. Now, this is where the intuition's really going to happen. And this is where you're gonna probably spend most of your time playing around with these types of proofs, is figuring out what string works that I can select under the assumption that is, in fact, part of the language. So I'm going to give you one suggestion, and hopefully I'll be able to motivate and explain it to you once we finish this example. I tried to give you some hindsight about it earlier. So I'm going to consider W. So I'm going to select W to be 0 to the P, as if I have two P stacked on each other. 0 to the P, 1 to the P. Which indeed is in fact a string in this language, right? We can all agree that this is in that language? Yeah, I think we're good. So keep in mind you have to pick a string that's in the language. You can't just fudge something up and be like, yeah, no, look, that's in the language, guys. Trust me, pros. You don't do that. Now, the one thing also you need to note is that I deliberately designed it so that the length is at least P, right? That you need. Since the length of W is at least P, then there is a way. Then there is a way to divide W so that W is equal to X, Y, Z, where W is not equal to the empty string, XY is less than or equal to the pumping length, and for all k are equal to 0, XY to the KZ is in fact in the language LEQ. So far we all good so far here. I've just laid out the conditions of the pumping lemma under the assumption that it should work for this string, right? Now, I want to just go a little bit one step further. Now, watch this. Now, this is where you got to be very careful. Since the length of XY is less than or equal to P, observe that XY consists, before I write this down, what should XY consist of? Is it going to contain any ones, or is it just all zeros? It's all zeros. That's, you see what I did here? That's why I designed the string like this. So I make sure that all the symbols that are going to be in that first part of the string are all zeros. This is going to make it easier for me to prove this claim, because remember, it has to work regardless of the way you decompose X, Y, and Z. And because I have this fact at my disposal, I can use this against the person positing that this thing is regular. Remember, think of it like a game. So, observe that XY consists solely of zeros. So it only consists of zeros. However, now this is where you're going to use this fact against this, is notice that Y has to be not empty. However, the length of Y is at least 1. Remember, it's not empty. So, if I take X, Y to the 0, Z consists of less zeros than ones. implying x, y to the 0, z, which of course is equal to xz, is not in LEQ, which is a contradiction. And of course that means therefore, that means the language LEQ is not regular. And that's the end of the proof. That box, it had a rough day. So notice here, so there's a couple of things I want. So first, are there any questions about this proof? So remember, I'm just taking on the fact that I'm assuming it's regular, so it means it has to satisfy the conditions of the pumping lemma. So what I do is I maliciously select a W that's going to cause some problems. So what I do is I show you that this W has a little bit of a problem. So I know it has a sufficient length. And then what I do is I select K. What was the value I selected for K in this proof? What was the value that I selected for K? Remember, K is in the last condition of the pumping lemma. It's 0. I heard it faintly. It's 0. I heard that. That was beautiful. That was beautiful. I loved it. Yeah, so notice that it's 0, which means that there exists. So if you think about that third condition, remember it said for all k greater or equal to 0, that means that x, y to the k, z is in the language. But if you negate that, it just means that there exists a k such that x, y to the k, z isn't in the language, and I've selected it right here. Now, notice that I use this one because notice that by selecting k to be 0, I axe off one of the zeros. So that means that there's going to be less zeros than ones, but this requires that there is an equal number of zeros and ones. Does everybody see that? So that's how I used k here. So by making it so it doesn't have y at all, I remove at least one zero. And because of that, it's not in this language anymore. Now, I want to just make a remark about this because I want to talk a little bit about how you can split these things. So I want to just kind of give you an intuition of where exactly I got the idea here in this proof. So where this idea came from. So that you could see how maybe you could try other values. So I just want to give you some tips on how to decompose x, y, and z and how I selected the way I did. So I just want to give you a couple tips. So just remember, you have no control of how x, y, and z get decomposed. So you have to be very careful. Remember, it has to work regardless of how x, y, and z are given to you. So your job is to design the string such that you protect yourself from a malicious. So if you're playing against somebody, they give you a really nasty looking decomposition of x, y, and z, you cover your butt by picking a string that causes them to pick probably the thing you want them to do. So I just want to give you an idea. So I just want to give you the idea here. We obtained a simple way any split can happen for arbitrary p greater or equal to 1. For arbitrary p greater or equal to 1. That is, so I'm just going to write it more carefully In fact, being more detailed is a good thing when it comes to these pumping lemma proofs, because often you have to convince the reader that indeed the string that I wrote over there doesn't actually belong to the language. This example is really simple, but you might want to be a bit more careful. So here's just an idea of how you could go about it if it was you wanted to be a little bit more careful. So just imagine I have the selection I did over there, like before. And I want to write it like this for you. So I'm going to take that 0 to the p, 1 to the p. I'm going to show you where the idea came from. So this part is x, this part is y, and this part is z. Because remember, there might be more zeros because all I know is that the y happens within the first p symbols. It may not necessarily be all p symbols. So where p is equal to a plus b plus c, the length xy is equal to a plus b, which is less than or equal to p. And of course, the length of y is at least 1. So those are the conditions I would like to have for this. So I want you to notice that I didn't necessarily have to pick k is equal to 0. So notice many different values for k. That says 4. For value k would have worked. Because you're going to find very often that you're be talking to somebody and like, hey, I use this value for k. What did you do? I don't know. I use this one. It's like, how'd you use that one? Sometimes there are multiple values you can use depending on the string that you select or just the general technique you choose to count the symbols. So here's just an example. Like say if I take k is equal to 0. So if I take k is equal to 0, the y part just drops out entirely. So I end up with it looking like 0 to the a plus c, 1 to the p. And of course, this means that a plus b is less than p. So it means it works. Because remember, the whole idea is we want to have the number of zeros be less than the number of ones. So this is actually how it worked in our proof. So if you wanted to be more exact than the way I wrote it over there, which I always encourage, you could have written this, and that would have worked. That would have actually been even clearer than the way I wrote it before. I just want to keep it simple. Okay, if I try k is equal to 2, this means I'm going to repeat y twice. Notice I'm going to get 0 to the a plus 2b plus c. So that's all in this exponent, concatenated with 1 to the p, where a plus 2b, so it's a plus 2b plus c is equal to p plus b, which is strictly bigger than p. So this works. So notice I could have used k is equal to 2. So I would have went x, y to y squared, z. And I could have used that as well. This will produce more zeros than ones. In fact, I want to go even more wild with you. Is that any k not equal to 1 actually works. So if you're not convinced by what I just wrote, I recommend trying to see what it looks like when we put k is equal to 1 into the above. You'll see quite quickly that, okay, well, you just get b, and then you have a plus b plus c like before, but that equals what? It equals p, right? So you don't get anything if you pick k is equal to 1. So notice that any k not equal to 1 will work here. So remember, we only require 1. That's all we need. We only need 1 k. That's it. We don't need to tell me all of the k's, just tell me 1. Remember, that's all I need to do. So just remember, the pumping lemma tells you there's some way to split the string. So when you're trying to refute this fact by producing a contradiction, you have to be considerate of the fact that somebody could give you some decomposition of the string, and you have to be prepared for any possible one they might give you. So the way you protect yourself is you carefully select the string W. So one common tip, like I mentioned, is pick a string so that all the symbols of those first P symbols are all the same. That way you can do something with that. So that makes me bring up a couple of smaller points. Just want to make a couple of remarks, just so that it's clear for everybody. So first, are we okay so far? I just want to make sure that I'm not losing anybody. I want to give you a couple more tips about this business. Then we'll do more examples. So the big point I'm getting at is that most of the time you're able to get away with selecting a very clever W. So I'm going to mention that for a lot of cases, try to select W. Try to select W. So that when divided by X, Y, Z, it is easy to determine. A good example of this is the exact example I use, and all the examples you're going to see, I'm going to try to do something kind of like this. Is that make X, Y all the same symbol. So that's the example. That's what I did with the previous example. So that will work often when you need an equal number of something, or there's maybe a side where you have to make sure that two sides match up, either from front to back or back to front. In the notes, I'm going to give you an example of such a thing where you're going to consider all palindromic or palindrome strings. Those are strings that you could read front to back, same as back to front. Just like you know the word race car, you could read race car front to back the same way you can read it from back to front. So those type of strings are not regular. At least the general language isn't. So another thing I just want to make sure, just to make this point really clear, be careful when selecting W. Make sure it is long enough. Because you need it to be at least the pumping length, right? So just as an example, if I gave you 0 to the floor of P over 2, 1 to the floor of P over 2, notice for certain values of P, this won't actually be long enough. So the length of W is less than P, except when P is even. So you would not want to select this W. It's not long enough. Now you might say, Dan, what if I round them up instead of rounding them down with these floor functions? The answer is you can do that. That's okay. So this is not okay. But if I wrote 0 to the ceiling of P over 2, 1 to the ceiling of P over 2. So remember, ceiling just simply means round up versus floor, which means round down. So if I take this, I can get this one is okay. But there's sort of a consequence with this one. So this, for the example we did before, I would not recommend picking this one. Does anybody see why I should maybe not pick this one? It will work. You just have to now consider something else now. So can somebody tell me why I maybe shouldn't pick this one as my W? Does anybody have any ideas? So what did I use in my proof before? I used the fact that all the first P symbols were zeros. So that eliminated the need for me to consider cases, except for just one. Would I have more than one case right here? Is it possible for P to consist of zeros and ones, for example? Sorry, not P, the Y. Can XY consist of zeros and ones? The answer is yes. So the answer is yes. So notice, so you need multiple cases here. So you're going to need multiple cases. Remember, notice that this will consist, there may be some ones there, there may not be. But the point is that notice that this isn't at least P symbols here. This is the ceiling of P over 2. So now there's a possibility that you're going to have to consider when there's ones there, and you'll have to yield contradictions for each one of these cases. So do you see why I picked the way I did as opposed to this? This is the first thing that people would try to do because they know that the pumping length the string has to be at least the pumping length. So some people would say, oh, let's try this first. This I would recommend against doing this, but it is a healthy exercise if you feel like challenging yourself. But I would not recommend it. You want to pick it so that XY consists possibly of the same symbol, or there's some other counting trick you can try using. So are y'all okay with that? These are just a couple of tips I wanted to give you with this. So if we're okay with this, I'm going to proceed to another example. So now we're going to go visiting around to something a little bit more number theoretic. So depending on how much time we have, we might do one more example next day. But I'll give you an extra example you can check out in the notes after. The one I mentioned about palindromes. I'll give you that example. And it also includes an idea for how to do another version of it. So let's do another example. So we're going to consider the following language. Consider LPR, so the language as follows. So I'm going to define it like this. So it's going to be all strings with 0 or more ones, such that the number of ones is prime. So I want to know, so any string that's going to be in here, the number of ones that have to appear has to end up, if I count them, it should be that it's a prime number. So for example, if I give you, say, this, that's in the language. That's in the language. However, 4 ones is not in the language. Does everybody understand? Are we all good? Don't be shy. Don't be shy. I feed on your reception. And also I like questions. Okay. So we're going to try proving that this isn't regular. This one's going to be a little bit craftier. LPR is not regular. So what is the thing I usually do? I assume that LPR is regular, right? Assume LPR is regular. Then what happens? Can somebody tell me, what do I have to do next? So what can I say if I know it's regular? There's a constant. Yeah, there's the P, exactly. The pumping length exists. Perfect. Then by the pumping lemma, there is constant P satisfying the conditions of the pumping lemma, right? That's what we get out of that. Now, I'm going to be very careful here on how I select the string. So this is going to first look a little ad hoc, as in something I just kind of cooked up. I just kind of like went to my magic bag of Dan treats and I grabbed it out and I said, "Hey, look, here you go. Here's some candy." This is one of those days. Consider some prime. Consider some prime m. I'm going to call it m, and it's going to be at least p plus 2. Remember, p is the pumping length. M exists. So I know m exists because of some elementary number theory, right? So m exists as there are infinitely many primes. So wherever I need a prime, I can find it. Infinitely many primes. So take note of the inequality I selected here. So notice that it's just that it has to be at least p plus 2. It doesn't have to be equal to p plus 2. Sorry, yeah, p plus 2. So now here's how I'm going to select it. So I'm going to let w equal 1 to the m. Ooh, 1 to the m. So notice I'm not using p here. It comes as a consequence of the previous statement. You're going to see how this is all going to play out in a moment. So what does that mean? I have selected it so at least the length of the pumping length, right? It's at least the pumping length. So, well, since the length of w is at least p, there is a way to divide w equals x, y, z so that y is not empty and the length of x, y is at most p. So what am I going to do? I'm just going to say for simplicity, I'm just going to write the length of y a little bit easier for myself. For simplicity, I'm going to let the length of y equal an integer d. Then I can rewrite the length of xz. Just if I take xz, I end up with m minus d. Because all I've done is I've removed y. That's where m minus d comes from. So I just removed the y part. And now watch how I'm going to inject this. So I'm going to take this number I computed and I'm going to inject this into the string. So follow carefully. So consider x, y to the m minus d, z, which is an LPR, which is in LPR by the pumping lemma. Well, you end up with this. Let me just do some algebra for you. And I'm going to put a couple of the details in the notes for the justification for this last step, but hopefully you should be able to follow me for this. So watch this carefully. So the length of x, y, y to the m minus d, z, this is going to be equal to x, the length of xz, plus the following. So now remember, the length of y is d, and I'm going to repeat it how many times? M minus d times. So I end up with m minus d times d. And now notice that this right here, this xz, that's m minus d. So I have m minus d plus m minus d times d. So it means I really just have one more m minus d. So that's no different than me writing m minus d times d plus 1, which has two factors, right? D plus 1 and m minus d. Now, the way this proof goes, because I want to wrap things up here, is that both of those factors are in fact, if you take a look in the notes, I give further justification for this, but you can show that both of those factors are greater than 1. So can somebody tell me, remember your number theory, is this a prime number or is this a composite number? So what's the result of this length? That length there? It's not prime, because notice both of the factors there, they're both larger than 1. And by definition, if it were prime, the factors would only be a 1 or the prime itself. So since they're both greater than 1, it has to be composite. And hence is composite. It's composite. It says composite. And since both are positive integers, implying that's not prime, so I'm just going to say this is not prime. That's not prime. So it's not in LPR, which is, of course, a contradiction. I apologize. The contradiction sort of wanted to go for a little walk. Therefore, LPR is not regular, because notice that I've shown you using this craftily created W that I can decompose it in a way so that if I select this middle part to be m minus d, that I end up getting something that ends up having a composite number of 1s in it, not a prime number anymore. And that's how I show that it's not regular. So that being said, I'm going to wrap things up here. I apologize for going a couple minutes over here. And I'll stick around for a couple questions if anybody has any questions, okay? So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.